Okay, so here's another group theory problem. So this one says, let G be a group and let big N be a normal subgroup of index little n. Show that G to the N is in the normal subgroup for all G and G. I don't think this proof is very long, so let's go ahead and get started. So proof, and we'll begin as always with our assumption. So we are going to let G be a group and N is a normal subgroup of G of index N. Okay, so since the index of N is of big N is little n, then that tells us that the order of the quotient group G mod N is going to be little n as well. Now it's important to note that since n is normal, then this quotient here does in fact form a group. And since it does form a group, then we know that if we take any element in this quotient group and we raise it to the n power, we will get back to the identity element. So that is, and let's recall that elements in this quotient group are just cosets. So that is for all, for every element in this quotient group, if we take the element and raise it to the n power, this is going to give us the identity element. And in this quotient group, the identity element is just going to be the normal subgroup n. But let's recall that what we have here is actually just equal to the coset G to the n operating on the left to the normal subgroup. And this implies exactly, if we take our equations here by transitivity, this is equal to the normal subgroup n. Now remember, these are just cosets here. So by our properties of cosets, this tells us that, so this happens if and only if G to the n is an n, which is exactly what we were looking for. So this completes the proof here. Now I did want to look at some examples that kind of, I guess, highlight or show this theorem in action. So if we take, for example, a group G, and we'll say that this is equal to, I don't know, we'll use the integers mod 6. Now the integers mod n in general form an abelian group under addition. So any subgroup of the integers mod 6 in this case will work as a normal subgroup. So for this example, we'll just take H to be the normal subgroup generated by 3, which of course is just going to consist of 0 and 3. Now this theorem that we just proved says that if we take any element, oh, you know what, let's actually write the index. So the index of H here, the index of H and G is going to be 3, because the integers mod 6 have order 6, this subgroup has order 2, so the index is 3. So what this theorem here is saying is that if we take any element in G and raise it to the third power, we will get either 0 or 3. So we can verify this very easily. 0 to the third, that's of course 0. 1 to the third is just 1 plus 1 plus 1, which is 3. 2 to the third is going to be 6, which is 0. 3 to the third is going to be 9, which is 3. 4 to the third is going to be 12, which is 0 mod 6. And then 5 to the third will be 15, which is 3 mod 6. And we can do just one more example as well. We can take the same, we'll use the integers mod 6 just for simplicity. But this time, let's take H to be the subgroup generated by 2 instead. So the subgroup will be 0, 2, and 4. And of course, In this case, the index of h in G is going to be 2. So this theorem says that if we take any element in the integers mod 6 and raise it to the second power, we should get either 0, 2, or 4. Again, 0 to the second is, of course, 0. 1 to the second is 2. 2 to the second. You can kind of see this very easy to verify, which is a very neat theorem. I didn't, honestly, when I was working this problem out, I did these examples first to kind of convince myself that it was actually true. And then I figured out the proof from there. Sorry, this is not 0. This is 2. And then this is 4. Okay, and then so that's the proof. And then some examples here.